But what we're going to talk about today is, what's changed, what's different. Engine blocks have changed, rings have changed, oils have changed, and all of that affects how the cylinders are honed and what we have to do to get the finishes that we want to get. So here we're going to kind of touch on a few things, and it's what's changed. Cylinders today are much harder than they used to be in the old days. Blocks back in the 70s, 80s, they were pretty soft, and you could get away with a lot of things. It was pretty easy to hone. The rings had a lot of tension to them. The coatings were very soft, and that's really not what we're dealing with today. So the blocks have changed a lot, and there's exotic coatings, and we'll touch on that stuff as we dig deeper into the program. Rings today, as we've all seen, much thinner, much lighter tensions than they were even 10 years ago. And then to go back 20, 30 years, much thinner materials, much lighter rings, and like I say, some really exotic coatings by comparison of what we used to have in the old days. Again, oils, much lighter viscosity. I can tell you my own vehicle, my own Chevy truck, 0.5, what are you, out of your mind? It's Arizona. It's hot out there. I had to put a 510 in it. I couldn't, I just couldn't do the 0.5. and what's the point of all this? We're trying to squeeze more energy from less fuel. So much of this technology is race driven, but it's also OE driven. They want to get less friction in the engine, which means more fuel efficiency, less tailpipe emissions. And it's the same thing out of the race world. We want to take that molecule of energy and extract everything we can. So if we can get the friction down in the engine, the rotating losses in the engine down, we're going to put more power to the drive shaft, more to the wheels, propellers, whatever it is that you're into. But if we can make that engine consume less of its own energy internally, we're going to have more to deliver to the output device. Ring materials. Again, we go back to the old days. Rings were always made out of irons. Typically from the early days, they were made out of cast irons. Cast irons are very soft, they're brittle, they break, they wear quickly, and don't handle temperature very well. Again, we deal with much higher heats today than we did in the old days. Much higher exhaust gas temperatures. We're dealing with unleaded fuels, and it's pretty easy to take a cast iron ring out in a high performance engine these days. So we really don't use a lot of cast irons. Ductile irons are still popular, still around, and they are very malleable, wear well, good flexibility. They're very durable, accept coatings fairly well, have good thermal transfer. Common coatings to see on a ductile iron ring are like chromes or moly. And I'll take a wave of hands. How many guys out there run a chromoly ring? Well, as a lot of us know, there is no such thing. The ring, what we're talking about is either the coating. It's either chrome or moly. It's not both. We're not dealing with tubing. So there were times when you had double chrome, meaning chrome top, chrome seconds. You had double moly sets, moly top, moly second. But today we pretty much run just a coated top ring and a non-coated second ring. So the whole chromoly thing is kind of, like I say, kind of a misunderstanding. Manufacturing iron rings have to be poured in large quantities, big castings. You got to go to a foundry. You have to have castings poured. So there's a lot of wasted material, a lot of scrap. And where that's going is, the industry's gone to steel. This is a quick shot of what iron rings look like. Rings either come out of what's called a ring cuff, kind of a casted piece, looks like a rough cylinder. You ID it, you OD it, you slice it, you dice it, or as you can see in the lower right corner, a ring tree, where they're casted very close to the sizes, basically the right IDs and ODs. If you look at that picture, you can actually see there's an inner and an outer ring, a smaller bore and a larger bore. So you'll take those pieces, you'll basically break them out of there like a model car kit, like a tree, and then again, ID, OD, heat treat, put the gaps in. But as you can see, there's a lot of machining involved. There's a lot of wasted material. Hence steel. I don't want to say we were the first people to get involved with using steel rings, but because I've seen steel rings all the way back into the 20s and 30s. But here in the States, we're one of the first. And what we found with steel is better durability. We use quite a few different steels here, from all different types of carbon steel, stainless steels, tool steels. We have some hybrid type materials. We actually work with a company called Metallurgy, which is a materials specialist. We actually have a copper-based alloy that we work with. So depending on the needs of the end user, there's different types of material, and what that comes down to is heat. I like to say heat puts the tension in, heat takes the tension out. So there's different temperature thresholds that we deal with depending on the material. So if I'm dealing with an extremely high temperature environment, we're going to have to look at materials like tool steel. And as Billy mentioned earlier, there's a lot of different grades of tool steel. We work with M2. On our stainless steels, we work with a material called 440B. And there's different temperature thresholds at which that part heat treats, and of course the heat puts the temperature, the tension in. Heat can take it out. So kind of depending on the application, we would need to deal with you, talk with you, and say what's the right material for what my application is. Thermal transfer is very good with the steels, similar to the irons. But with steel rings, we open up a whole range of different coatings that can go on there, particularly PVD style coatings, mollies, CRNs, C72 titanium nitrides. We'll get into that a little later. The biggest thing about steel rings is the manufacturing process. We can do it out of coiled steel. Instead of having to pour the material, machine the material like that, we actually comes out of a coil of wire. So I actually have videos on our website you can look at, and I've got some actually on my laptop we could probably show later, but that's what a steel ring comes out of. It actually comes out of a big spool of wire. So when we do it, we actually cam coil the material. So there's very little scrap. I can actually cam coil that one ring, produce one ring. Instead of all this machine material that's left over, I end up with that one ring with very, very little scrap. So very little material has to be recycled. And in the big picture of things, it ultimately helps keep the cost down. So rings have changed from iron-based parts into steel-based parts because we can do thinner rings, lighter rings. It'll accept coatings that iron-based rings don't like to use. And again, helps keep the manufacturing cost down. And this is just kind of a visual representation of ring thicknesses. These are actually to scale. So you can see on the very bottom row, we've got the 1/16, the 1/16, and the 3/16, which just a few years ago was considered the thin ring package. Then we've got the more modern 1 millimeter, 1 millimeter, 2 millimeter, which has become very popular, much lower friction, much lower drag, better bore conformability. And then even smaller than that, the 0.9 millimeter, 0.92 millimeter combination that we offer. Very nice ring package, very low drag, excellent bore conformability, less mass. And today we're doing rings as thin as 0.5 millimeters. So if you put that into thousandths of an inch, you're only talking 20 thousandths of an inch. Very small. It's about the size of an oil ring rail that would be on that 3/16 oil ring. So if you kind of put that into perspective, that's actually a compression ring that we do today, and they hold up very well. And that's because of the material technologies that are available today. Excuse me, I've got an itch. Wanted to show you this graph, and it kind of talks about ring tensions. And again, trying to show a little bit of history of where rings have gone. A 5/64 ring, and these were all done at 4/185 bore, by the way. The 5/64 ring with 190 depth, ductile moly ring, checking at about 7.3 pounds of tension, 7.5 pounds. And as you can see, as you're going smaller and smaller, lower and lower, the ring tension goes down significantly, all the way down to like a 0.7 millimeter ring, where we're down to about a 0.5 pound of tension, 0.7 pounds of tension, extremely light, extremely low friction, extremely light load on the cylinder wall. So it really significantly reduces bore wear. The rings last longer. People have a tendency to think that, thinner rings don't hold up very well. Wow. I mean, they're, again, like I said, there's guys that are still thinking the 16th ring is the little guy. And it's actually kind of the opposite of what you think, or a lot of people think. As you get into the thinner rings, they're much, much easier on the cylinders. They don't wear as poorly. They don't wear the bore. I have many, many race applications out there today that are going in excess of 4,000 race miles on 0.6, 0.7 mil rings, because again, they're so easy on the bores, they're so light on the wear, they just don't wear the parts out. And you can look at the bottom part of the page, looking at oil ring tensions, and I want to kind of touch on this in particular, because there's kind of a little bit of a misunderstanding out there in the industry, and I want to take a moment to correct this. Again, this has nothing to do with cylinder honing, but I want you to be aware of this. Oil ring tensions. A common statement that's used is standard tension or low tension. And what you have to remember is those standards are relative to the size of the part. What is standard tension? Well, a standard tension 3/16 oil ring is typically in the 20 to 25 pound range. A low tension 3/16 oil ring is typically in around the 15 to 16 pound range. And that's pound force. That's what it puts against the cylinder wall, not sliding friction up and down the cylinder that we would check with a fish scale. A lot of guys use that because that's the equipment that's available to them. So they'll fish scale and kind of look at sliding friction, which is a little different than how we test it. We actually test the tension or the force that it takes to compress it down to that size. But if you look at the next level down, the next line down, I should say, the 3 millimeter. I get this thrown at me all the time. I want a standard 3 millimeter. So it comes back to the question of what are you referring to as a standard 3 millimeter? A standard 3 millimeter is about 10 pounds. So are you asking for a 3 millimeter that's the standard for a 3, or are you asking for a 3 that's about the same as a 3/16? So you have to be careful with words standard tension, because standard is relative to the size of the part. Same thing with a 2 millimeter oil ring. A 2 millimeter oil ring is typically about 7 to 8 pounds. That's standard for a 2 millimeter. Now we can make 2 millimeter and 3 millimeter, they're much higher. We can make them much lower. So it's really kind of a matter of knowing what your application is and how much oil ring tension does it need. You know, if it's a street car driving every day, wet sump engine, you're probably going to want something more than 9 or 10, especially in an engine like a small Chevy, big Chevy that was designed around a much, much higher tension oil ring. You go back to oil flow, oil volumes, how much oil is being thrown around inside that engine. And there's many chances, many cases where it's going to take a higher tension oil ring to keep that engine dry. So just wanted to kind of hit on that real quick, just to be aware of what standard tension means. And it doesn't mean it's always the same number. It doesn't mean it's a 20-pound oil ring across the board. It means it's standard for the size of the part. Lake had talked about it a little earlier in his presentation, showed you some hardness numbers. And these are some illustrations of actual ring face coatings. And in the upper left, as you can see, we've got cast iron with no coating. Fairly porous area, but no anti-friction, no anti-wear, very soft material. The one I want to kind of concentrate on, though, is the one in the middle top, molybdenum. It's about 800 Vickers hardness. And one of the unique characteristics about molybdenum is it's very oleophilic. It holds oil like a sponge. So keep that in mind as we move forward in the presentation about what the coating itself does, not only is from a friction point of view, but from a lubrication point of view. How well does that part hold oil? Next one to the upper right is electrofusion or hard chrome. That's a plated chrome, just like a bumper on a 57 Chevy or Cadillac, or had your wheels done in chrome. That's your electroplated chrome. Those types of coatings, fairly lumpy, fairly bumpy, kind of old school. They do work. They work fairly well. There's fairly good anti-rust characteristics, anti-friction characteristics, but it's not the easiest seating, quickest seating. It's hard to get it really uniform and really nice and flat. It doesn't want to mirror the substrate of the ring extremely well. Now you go to the lower row of coatings, and now you're into the PVD type coatings. And lower left is tungsten carbide carbon. One of the things Lake had touched on earlier was how long, you've got to kind of look at the duty cycle of the engine. How long is it going to run? The WCC coating is an extremely low coefficient of friction coating. It's a 0.1. So it's a very, very low friction coating, but it's in the big scale of things a little on the softer side. So if that's a coating or an application that I want to get 10,000 race miles out of, probably not going to be the right coating. Probably going to wear, but it's going to seep very, very quickly. So you always have to kind of look at the coating and what the application is going to be. Next one's chromium nitride. Very, very common coating today, very popular. About the middle of the scale as far as hardness goes on PVD type coatings, about 1,700 Vickers. Little higher coefficient of friction. I think off the top of my head, it's about a 0.4. Wears very well. Common coating to see put on stainless, on valve stems, on valve guides. Not guides, but valve stems. And then you work your way up the scale into the titanium. Titanium nitride, about 2,400. Harder coating, gonna last longer. Similar coefficient of friction to the chrome nitride, but ultimately it's gonna take a little bit longer to seat up. It is a harder coating, but wears better. And again, into the diamond-like carbon on the higher end of the scale. That coating can be in excess of 3,000. Again, not all DLCs are the same. And as Lake said earlier, some are really good, some are really bad. Adhesion can be an issue with DLC. You don't want that coming off inside the engine. There's a billion little tiny razor blades, diamond-like, flying around inside your engine. So you got to be careful with DLCs. A great DLC or a good DLC is a nice coating. It wears well. Again, low friction characteristics, but it can come off. And if it does, you don't want that flying around inside your engine. Next, we're going to talk about the actual cylinder itself, the hardness of the block. So we've talked about the ring. Ring materials are harder. We're into harder coatings than we used to be before, much harder coatings than we used to be before. But then you've got the cylinder itself, the actual cylinder wall that we're working with. And again, typical traditional old small block Chevy, small block Fords, Mopars, your typical gray iron cylinder, as you can see in the upper left picture, hardness scale. And again, we're jumping from coatings. We're looking at Vickers. Now we're into Brunel. Cast iron, you're typically in the 150, 180 range on a cast iron block. And you can also look at the grain structure in the material, how it looks like little grains of rice. There's lots of little pockets, lots of little places and little pores to hold oil and retain oil. And all of this is about oil retention. Everything we're doing here and talking about is keeping that oil interface between the cylinder wall and the ring itself. Rings ride on that film of oil, and it's very important that we retain that. We start getting into the newer blocks, the dart blocks, bow tie blocks, your world blocks, and we start moving into numbers into the low 200s, 200, 250. We're dealing with a fairly big jump in hardness of the cylinder. So it does become a little harder to hone, a little harder to machine. But if you'll also notice, the grain structure is changing. It's changing significantly. We're going from that, more rice-like, more grain-like style structure into a more pearled or rounded structure, less pockets, less pores. We've all looked at gray iron. For those that are into iron, cooking utensils, pans, you oil that pan, you season that pan, you're getting that oil, that iron to actually hold oil on its surface to create that cooking surface. And that's because that material is relatively soft and it's porous. As we go up in hardness, the cylinder doesn't want to hold that oil anymore. It gets to a point where it actually wants to start to reject that oil. Then we start getting into the even more modern type stuff, the hybrid, the hardened ductiles, compacted graphites, the later model Darton sleeves, LA sleeves. Some of the dart blocks, we're pushing numbers in excess of 300 today. Much, much denser material, much more difficult to hone, doesn't want to hold oil as well. And then you get into more exotics, which we'll talk about later in the program. Coated bores. There's steel cylinders out there today. I've seen cylinders in excess of 550 Brunel today. People building cylinders out of, we talked about chromoly, building cylinders out of chromoly, trying to get that stiffer cylinder, which makes it just that much more difficult to hone. But it can be done with the right tools. And all of this comes down to the need to measure surface roughness. As you can see, as we talked about before, we're dealing with a much wider range of hardness in cylinders. You jump back again to the 1970s, you're dealing with blocks that are all traditionally about the same hardness. We're dealing with relatively thick rings, big 5/64 rings with 20-pound oil rings. You can get away with a lot of things when you're dealing with relatively soft blocks and relatively hard, relatively soft rings, soft blocks, high tensions, excuse me. You can get away with a lot of things. The rings will correct an incorrect cylinder finish kind of on their own. Rings naturally plateau cylinders. But in today's world, where we're dealing with very light tension rings, hard coatings, and hard blocks, we're not going to get that wear that we would get essentially or initially with the softer blocks and the bigger rings. So it's a matter of having the tools available so we can actually measure those surface finishes. And again, as mentioned earlier, Billy had a real nice point. One of the most common numbers to use is RA, arithmetic average of roughness. The problem with RA is it's a big blend of numbers. And you can have what would have traditionally been looked at as a great RA and still have a horrible cylinder finish. And here's kind of an example of that. This is not as technical as what Billy put out there. And again, I keep mentioning my other speakers, but I don't want to some of what they presented was, or all of what they presented is really good, and covered a lot of what I'm talking about here. But here's some visual examples of two different surface finishes that both measure the same RA, but have two completely and totally functionally different characteristics. The upper surface, as you can see, has a beautiful plateau right across the top. My little pointer right here. Great low profile surface. And the surface down at the bottom, which is completely inverted, has nothing but peaks, no valleys. And using RA, they're measuring the same. using just a simple, pocket surf or something like that will only measure RA, you can have a great surface finish number, but have an effectively, horrible surface finish. So that's why we don't use RA. And again, this is kind of a reflection of the same surface finish we just looked at. The above up here, if you can see the pointer, we've got no plateau, got lots of peaks. This is our RK, this is our core value, this is our valley, but we don't have what we've got down here, a nice plateau, that nice flattened out surface finish. And that's what's essential to getting good, quick ring seal today with thin rings, hard coatings, and hard blocks. As I said earlier, rings naturally plateau bores. They do that through the running in process. So back when you had soft blocks, soft rings, lots of tension, you could have a surface finish that didn't really have a lot of plateau. And through the running in process, those guys that have been around a while, like myself and some of the other people out there, I'm sure, remember the old days. It might take you 2,000 miles, 3,000 miles to wear to get a set of rings to completely seat up. And people would say, well, that's the ring. Well, sometimes it's ring, but generally it was a cylinder finish issue. The cylinder simply didn't have a good plateau. And it takes time for that ring to wear that plateau in. And it will do that naturally through the running process. And again, with soft blocks, softer rings, big rings, lots of tension, it's going to do it relatively quickly, but not so much with today's stuff. That's why it's so very, very important to have access to one of these, the profilometer, so you can actually measure that finish and make sure you're getting that plateau. This is the same slide that Lake showed earlier, and why I'm touching on this is rings ride on that film of oil, and it's so important to get that proper amount of oil retention on the bore, especially in high cylinder pressure applications, applications that are have a lot of fuel going through there, trying to break the oil film down, getting into a lot of oil dilution, everything that's trying to kill that oil film, high vacuum situations. Not uncommon today to see engines that run 20, 22 inches of vacuum in the crankcase. All that vacuum is doing is trying to pull all that lubrication off the cylinder wall away from the ring. During that ring reversal time, top and bottom dead center, when, as Lake indicated, the piston stops, everything slows down like that ski on water. It's coming off plane and sinking through the oil, through that lubricating area. We've got to have that oil retention and keep that oil film to keep that ring lubricated, the piston lubricated. If we don't get that, we're going to get into that heavily loaded area. We're actually going to get that metal to metal contact, and we're going to see that we're going to see premature ring scuffing, cylinders that aren't happy, pistons that aren't happy, and it's because we're losing that lubrication. About 90% of the failures that I see customers sending me rings almost always come down to some sort of a lack of lubrication to the part. The ring itself is really a pretty simple piece. If I make it round, I make it flat, I make it light tight, I make it the best I can possibly make it, I really can't do more with that part. So if I put the part into an environment where I've got an excessive amount of fuel, I don't have that lubrication of the part, that oil film that creates that gasket, that sealing surface between the ring and the cylinder wall, we're going to have that failure. And I get the part in and I look at it, it's simply a lack of lubrication of the part. There's a lot of things that can do that to the ring, but that getting that cylinder finish right for that application is so important. It's the first step to eliminating that issue. This slide talks about pressure, and this is where we're talking about plateau honing. So if you can kind of follow the cursor, no plateau at all. So we're going to say that ring's producing 500 pounds per square inch of force against that cylinder wall. So with no plateau, I've got 100% contact. I've got 500 pounds per square inch of force pushing against the wall. No ability to lubricate, no ability to keep that ring suspended up off the cylinder. It's going to have full contact, and we're going to have a disaster area in a heartbeat, just like a bearing on a crankshaft with no oil. It's not going to last very long. As we come over to this slide shows almost no plateau, about 10% plateau. So now, instead of having that pressure spread out across that area, I'm sitting just on the peaks. I'm sitting on those points, on those tips. And during initial fire up, during that initial startup, with that much pressure against the ring on that cylinder wall, we're going to get it's just kind of like a razor blade against it. We're going to get into a lot of scuffing. So we're not only going to wear the ring, we're going to wear the bore, and we're going to create a lot of debris that's going to get into the ring groove, into the skirt of the piston, into the oil pan. We've all had those engines we've taken apart, and you see that layer of stuff down in the bottom of the pan, and you kind of grab it up and it's a little bit sparkly. That's your cylinder wall. More than likely, you had a cylinder that was honed too rough. It didn't have a lot of plateau, and through the running in process, again, the ring's naturally going to plateau that bore over time. We've ended up with all that material down in the pan. Well, that's, you know, prematurely worn block, prematurely worn ring, a lot of scuffing on the part, and almost always going to cause a delay or, you know, accelerate the wear process in the engine. As we come over to this slide, you've got about 40% plateau. And that's reduced the pressure on the ring from 5,000 pounds per square inch down to about 1,250 pounds per square inch. Again, less wear on the ring, less wear on the bore. We're ultimately going to achieve that plateau on the cylinder quicker, and we're going to have that ring seal that comes in faster. If you're on the dyno and you've got one of those engines that, you know, it's like, hey, I get guys all the time on the phone, you know, hey, we're 10 poles in, we're 13 poles in, man, she's really starting to come in. The power numbers are starting to come up, the blow-by is starting to drop. That tells me right off the bat that we didn't have a good plateau on the cylinder finish, because the ring, again, we're back to, it's doing the plateauing, it's doing the wearing, it's bringing that surface down, and every pole we put on it, it's doing that job more and more and more, and we're flattening that out, we're flattening the curve, we're flattening it out and creating that plateau. And the power numbers are coming up, the oil consumption's going down, blow-by numbers are coming down. It's because we're creating that plateau. But the ring's doing the job. If we've got a really well plateaued cylinder, it's going to come in almost immediately. You're going to have that engine on the dyno, it's going to go 1, 2, maybe 3 hits. You're going to have that great ring seal, fantastic blow-by numbers, dry as a bone. That tells you right there, you've got a really, really good cylinder finish. If you've got to keep beating on the thing an excessive amount, that's almost always an indication that there's something wrong with the cylinder finish. Generally speaking, way too rough. Doesn't have a plateau, even though you think it does, or you were told it does. So to the right slide here, we're looking at about what we're looking for in a properly plateaued cylinder. We want about 80% plateau. So about 80% of the surface flattened out. You look at the pressure numbers, we're down to about 625 pounds per square inch. Very few peaks, a lot of plateau, nice valleys. Kind of going back to the numbers we talked about earlier, RA. There's numbers that can be used. They're RA, RZ, which is your peak to valley height spread over 5 segment lengths. Then there's also a thing called the Abbott-Firestone curve, which is commonly seen on older profilometers. New ones will do it too, but you know, the new ones will measure other numbers that we'll talk about in a second. But if you look at your Firestone curve, your what are known as your MR1s and your MR2s, you can look at those ratios. And when you're seeing your MR2 numbers sitting up and around that high 70s, low 80s, that's representing your surface finish, how much plateau it does or doesn't have, how much material is above the curve, how much material is below the curve. So if you don't have a proper, a profilometer that will measure the newer types of numbers, you can work with the older numbers as long as you can measure the MR1 and the MR2. Went one too far. So what we're looking for today and what we're measuring today are referred to as the following: RPK, RK, and RVK. And RPK is, as it says, reduced peak height, measures the portion of the surface's protruding peaks that will wear during initial loading. What that means, in essence, is that's the surface that the ring is going to touch when the engine's first fired up. When you first build that engine, that's the peak that's sticking through the film of oil. That's the part that's actually going to come into contact. So if we get a high RPK number, we're going to have a lot of wear metals that are going to occur. We're going to have scuffing in the ring. We're going to wear the cylinder bore. We're going to get that material into the ring groove. That can create micro welding. We don't want to see a really, really high RPK number. At the same time, we don't want a really low number either. We need there to be again, kind of like cooking or any kind of a recipe, just the right amount. We want enough roughness on there to get the ring to bed in. Again, that break-in process is really the final machining process. That's the last step in getting that engine, the cylinder finish just right. We can only do so much with the hone. We can get it as perfect as we can, but there's still a little more to go. We've got to have that little bit of wear, that little bit of roughness, that little bit of friction when we first fire the engine up to get those surfaces perfectly made up, just like a flat tappet cam to a lifter or a brake pad to a brake rotor. Got to have that little bit of friction right there to get the surface to perfectly made up. The next number is the RK. That's the core value. Core roughness depth is used to describe the portion of the area that will support the load. And what that is, that's the bearing area. Why we don't use RA is it doesn't refer to the ability to bear a load. It has no reference on load bearing. Using these numbers, we can look at the peak roughness, the core roughness, and that valley roughness. And now we can describe the ability of that surface to support and bear a load. And we talked about the ring and that oil film. Well, you've got thousands of pounds of pressure that are trying to push that ring through that oil film and push that ring into the cylinder wall. If we've got the right amount of oil storage, the right amount of roughness, the right amount of bearing area for the application, that's not going to happen. The ring's going to stay on that film, and it's going to stay on top of that film, and we're not going to get that scuffing, that premature wear, and we're going to have excellent ring seal. The next value is RVK, and that's the valley depth. Valleys protruding through the roughness core value is the oil retaining portion or the troughs machined into the cylinder surface. That's your valley depth. What that speaks to, and I like to refer to it as a rung on a ladder. Just because we're throwing oil into the cylinder, we can have oil jets, we can have all kinds of volume. Just because we're throwing that oil up into the board doesn't mean the oil is going to stay there. It's the ring's job to take that oil, scrape that oil back down into the sump, and create, again, just that right amount of oil on the board to keep that part supported and not have metal-to-metal contact. If we don't get that depth, that RVK, the oil's not going to have anything to cling to hold onto and get a grip on. And the RVK is probably the number I see missed the most in cylinder honing. We go too far, we plateau too much, we lose that valley, and that's the most common number that I see that gets messed up. If we don't have that ability to retain oil, like I say, it's kind of like that rung on the ladder. Anybody ever played that game Crazy Climber? We're trying to climb up the side of the building. Well, it's hard to get a grip on there when the window's closed. And if we don't have that depth, it doesn't give that oil that ability to grab a hold of the board and cling to the board, stay on the board. It ends up back in the oil pan, which is a good place for it, but we got to have the right amount of it on the cylinder wall to keep the rings lubricated. To look at all these numbers and measure all these numbers, we're going to have a profilometer. I use a Mitutoyo SJ210. It's a very popular piece of equipment. Measures a lot of parameters. The machines will do more parameters than you could probably ever use. But it will measure all the numbers that we needed to use. So that's a great machine. Whether you use a Mitutoyo or you don't use a Mitutoyo, that's neither here nor there. But you really want to have a machine at your disposal or access that will measure RPK, RK, RVK. RA is nice to have for non-moving surfaces like gasket surface, deck surfaces on cylinder heads, making sure that you've got that head gasket sealed up nice. But the RPK, RK, RVK are really the numbers that we've got to look at when we get into cylinder honing. And these are some target numbers that we want to look at when we're doing that honing. When we're getting into real thin rings, excuse me, I'm just kind of looking at my numbers here, and I've already gone over a bit, and I apologize for that. Real thin rings, 0.8 millimeter stuff, 0.6, 0.5s. We're looking for a target number of about a 10 on our peak roughness. RK numbers, we're looking at for about a target of a 25. May RVK about a 35. But there's always a window. It's always you can have a little bit higher, a little bit lower. We want to kind of watch we have target numbers. General purpose stuff, and this is 99% of what's out there. Circle track, drag race, bracket race, street cars, daily drivers. RPK number, we're looking for a target of about a 15. My core value about a 40. and my valley depth about a 50. We get into high cylinder pressure applications, big boost, big nitrous, big turbo. Same thing. Peak value stays about the same. I want to see about a 15. Again, that's that roughness that the ring's going to touch when it first fires up. 10 to 15 kind of seems to be a real sweet spot. Brings the rings in nice, seats up really quick, but it's not hard on stuff. Doesn't create a lot of debris, a lot of junk. I want to bring that RK value up. That's my bearing area. I want to bring that up because it's going to support more load. And I want to bring the valley area. That's that oil retention. That's ability for that oil to cling to the bore. Now, these are good general numbers, but there are times where you're going to need higher than this. I have a very good customer of mine, builds real big diesel stuff, 4,300, 4,500 horsepower, big diesel, big pulling diesels. They're pouring so much fuel through this engine. He has spent thousands and thousands of dollars on different cylinders, as far as the materials, different types of hone, different ring coatings, and everything we see, we're always seeing this lack of lubrication, no matter what we do, material-wise, coating-wise. So, we talked about it quite a bit. I know Lake was involved with speaking with him, and we just started bringing that RVK and the RK numbers up. He literally got the RK values a little over 100 and the RVK numbers up into the 140s. Very, very high numbers, but a lot of oil retention, a lot of oil trapping. These guys pour everything through this thing, including the kitchen sink. I mean, it's diesel, alcohol, water. You're pouring all this fuel through this engine to the point that rust has become a problem in it. But getting those numbers up that high is what it took to keep the oil on the cylinder wall with that much fuel going through it. And guess what? All his ring seal problems went away. All the wear went away. Problem solved. It was simply cylinder finish. He's putting so much fuel through the engine, it's washing the oil film off the bore. So these are good general purpose numbers and all around good targets depending on your application, but they're not the be all end all. So I always say, hey, reach out to us. Get a hold of myself. Get a hold of any of the guys here. Discuss your application with us, and we'll help point you the right direction. The one thing that there really isn't out there is a flow chart. There's Rottler equipment, Sun equipment, Winona, Surdy, AN style heads, Diamond style heads. There's so many different types of materials and abrasives out there. The days where I could just give you a flow chart and say, do this, do this, do this, and you're going to get that finished. Those days are kind of long gone. I do have information on the website. It's good general information to help point you that direction. But that one-on-one interaction where we can actually talk about what you're using, what kind of equipment, what's the application, we can help guide you down that pathway a little bit better. I really wish, like I said, that somebody could produce just a piece of paper to give you to say, hey, do this, and that's what you're going to get. But anybody that tells you that's a flat outlier because there's just too many variables. One of them being this. This is the surface finish generated by a vitrified stone. Most common stone out there, been around forever. You can see very nice, clean cuts, not a lot of debris, not a lot of junk. You can see fairly defined finishes, fairly defined surfaces there. That's a 280 grit vitrified stone. But here's the next stone as a comparison. And this is why, again, it's really difficult to put a chart together that says, use this stone with this pressure on this, and you're going to achieve that, because we've got all the variables of block hardnesses, stone, coolant versus water, oil. All of these things make a difference when it comes to that surface finish. That's a similar grit diamond. As you can see, two completely different surface finishes. You've got the cuts, but you see the little dark spots. That's a lot of burnished material. Didn't cut really well, kind of rolled the material over versus cutting the material. And one of the things you have to be careful about when you're honing is you can falsely get good numbers when you're honing if it rolls that peak over. It didn't cut the peak off, it rolled the peak over. And you can actually get a good surface finish number and actually have a bad finish if it rolled that peak over, if you burnish that cylinder. But that's something you can pretty much see, and I'll have an illustration of that here in just a moment. And this is kind of the next thing that's, I'll call it, coming up in the surface finish or in the honing world, is CBN, cubic boron nitride. We've been using it for years, and in all kinds of cutters, or cylinder deck surfaces, valves, valve seats, and it's kind of working its way into the honing world now. What we're finding is it cuts very, very well. It cuts like a vitrified. leaves a very clean, very nice surface. You can see the nice lines, consistent crosshatch it produces, not a lot of tore up junk, not a lot of burnished area, but it lasts like a diamond. So in today's modern machines, when you plug in a number and tell you want to take 5 thousandths out of the cylinder, and that's kind of why super abrasives work the way they do, is they don't break down a lot. Vitrified stones break down fairly quick and keep really clean, sharp abrasive. But it's hard to put that in one of today's computerized machines and tell it to take 5 thousandths out of the cylinder wall. It doesn't know if 5 thou came off the stone or 5 thou came off the block. It just knows it changed size. So with today's super abrasives, you really don't want the stone to break down much. And that can create an issue. That can load up stones and again, create burnished cylinder walls. You get that dark look. And so the look of the cylinder really comes into play. And again, we'll show that here in just a moment. But super abrasives are changing and you're getting where they break down a little bit more and the bonding agents are a little bit different. And CBN is kind of one of the newest ones that's coming out. And I really like the CBN. Diamonds work well, vitrifieds work well, but I'm really kind of a fan of the CBN. So if you're looking at stones, talk to your supplier about CBN. I'm really seeing some remarkable surface finishes produced by CBN. That's one of the things you should see when you're done honing a cylinder. Now in this particular case, that's actually a Nicosil cylinder. But what you see is a very bright, very sparkly, very shiny cylinder. Cylinders should always have that nice, bright, shiny, sparkly look to it. It shouldn't be dark. It shouldn't be dull. It shouldn't be gray. That dark gray, nasty, you get that real black looking cylinder. That's a burnished cylinder. When you're done honing a cylinder, it should always go out, look bright, shiny, sparkly, brilliant. It should always reflect light back. You should have that look of the rainbow colors like a diamond would. And that's a really good cylinder finish. So use the tools that you've been equipped with, your eyes, and look at that cylinder finish. If it looks dark, it looks dull, it's got that blackish look to it, it's most likely burnished. It's rolled the metal over. And even though you have a profilometer and even though you can measure those surface finishes, you can falsely get a low RPK number because it rolled the metal over. But it won't fool on the look. The look is always important. You should always have that bright, shiny, sparkly cylinder. One of the most common things I see in honing today, and where guys get the numbers messed up, I'm actually gonna back up a little bit here and go back to those numbers. The most common thing I see today is RVK values are too low. They'll get the RVK and the RK flip-flop. They'll get them backwards. And generally what does that is too many steps in the honing process. In most cases, you're going to have a roughing step. You're going to get it really, really close to size. You're going to have a sizing step, and they'll refer to as a finishing step. I'll get guys that'll bring it to size, leave it within 5 thousandths, say using a 220 grit stone. Then they'll come back in, use a 280 to get it within 2/10 of size. Then they'll come back in, use a 400 to get it to size. Then they'll come back in, use a set of brushes and stroke it, 10, 15, 20 strokes. Well, these numbers that we're looking at here, these 30s, 40s, 45s, we're talking micro inches. These are very, very small cuts. And it's very easy to lose that valley number very, very quickly when we start introducing a lot of steps into the honing process. Honing should be pretty straightforward. What I want to call less is more. A roughing step, a sizing step, and a finishing step. And on the finishing step, it's almost always better to leave it a bit rougher. On these numbers, let's just say for my general purpose number, I'm looking to get an RVK of a 45 to a 55. Well, when I start plateauing, what I like to do when I'm using my profilometer is I'll stop before I start plateauing, whatever that function be for you, whether that be with a fine grit abrasive, a ball hone, one of my favorites, or brushes. There's a lot of different ways to get there. It's like, we'll say getting to your house, probably 5 different ways to get there, but the end result is that you got there, you got the numbers. If we start off with that RVK number too low to begin with, it's only going to go lower. So if I'm trying to get a target of say a 50, that window of 45 to 55, before I start my plateauing process, I better be in the 60s or 70s. It's almost always better to have that number be higher than lower because it's only going to go lower when you're plateauing. So if you've got that profilometer, stop at that step before you start plateauing and take that look at that RVK number. At that point, That's really the only number I'm really concerned with is the RVK. If I want to be a 50 at the end, when I'm plateauing, I better be starting off around a 70 because that number's only coming down. Now we can come in and start plateauing with whatever tool we're going to use, a fine grit abrasive, a ball hone, brushes, and we can start going at it slowly. Come in, lighten the pressure up, 4 or 5 strokes, check it. We're not there yet on the peak and the core value, a couple more strokes, check it. Work your way along the line, but keep checking it. Don't wait till you're finished to check the numbers. You may have gone too far, and it's almost always a matter of losing that valley number. So important to keep that RVK number up, to keep that oil retention, to keep that oil trapping, the bearing area, the RK, the RVK, the oil retention area. Those numbers, I see it get flip-flopped so many times. We get into premature wear, bad ring seal, too much blow-by, oil control issues, all the bad things. Keeping those numbers up high, assure that proper ring seal. So just wanted to kind of touch on that. Many steps in the honing process is almost always a key to disaster. This is kind of a less is more. Rough it, bring it to size, hit it with a plateauing tool, whichever that one is of your choice, and then hit those numbers, checking them along the way as we go. Gonna spring back forward. This is Nicosil, and Nicosil has become very common today. Again, we've been talking about iron cylinders, but in today's world, there's a lot of exotic materials coming out. Nicosils are very popular, especially in motorcycle applications. Nicosil is a nickel silicon carbide. So as Lake said earlier, you don't want to put basically chrome on chrome. It likes most PVD coatings. Chrome nitride, titanium nitride work very well on it. But you don't want to put any kind of hard chromes against it. They're very similar materials, and alike materials generally don't work together, and you can get into adhesion problems. They'll try to pull the Nicosil right off the board, and that's always bad. One of the things about Nicosil, and it's kind of easy to tell, and this is another little trick for any kind of surface. When you look at Nicosil, you should see that really nice pronounced crosshatch, but kind of an easy test is what I want to call the fingernail test. If you don't have a profilometer, run your fingernails up and down that cylinder. You should see a nice pronounced crosshatch, very visible, very there, but it should feel glass smooth. You should almost not feel, you should see the crosshatch, but you'd almost not feel the crosshatch. That's proper Nicosil. If that cylinder feels rough to you, it is rough. And Nicosil being, again, what it is, a real rough Nicosil bore is most likely going to tear the rings up when it starts because it's so sharp, it's so hard. The rings, like we talked about earlier, will naturally plateau it down, but by the time it does that, it's going to destroy the rings. It'll literally chew them right out of the engine. So Nicosil should be very smooth, like glass, though you should see the crosshatch pattern. And the same thing kind of applies to an iron bore. You should see that beautiful crosshatch pattern, nice and uniform. When you run your fingernails up and down it, again, not a profilometer, not a true test, but that simple kind of a feel. You should feel the crosshatch, but it should not feel like a fingernail file. If it feels rough to you, it is rough to you. And if it feels rough to you, it's going to feel rough to the rings, and it's going to tear the rings up when you first fire that engine up. And that junk that's going to come off of there, it's going to get in the ring grooves, it's going to get in the skirts, it's going to get into the pan, and it's going to create wear problems. It can create micro-oiling problems between the ring and the ring groove. I have a customer that's been fighting an issue. When he hones with a vitrified stone, he doesn't have a problem. But he switched to diamonds, and he's still kind of learning the diamonds. And it's come down to he's leaving a lot of junk. He's leaving the cylinders a little too rough with his diamonds. So when he breaks the engines in, he's getting that junk, he's getting that grit, that abrasive into the ring groove, and he's having a micro-welding problem. And it's not the fault of the diamond, it's not the fault of the ring or the piston, it's just his surface finish. He's worked on it now, he's got those numbers down, that problem's gone, but he was just leaving so much junk on the board, that rough metal, which it shouldn't be there. Another one of the things that's out today and very common is the arc plasma sprayed bore. These are becoming very popular. Ford's using it, Nissan's using it, Toyota's using it, Mercedes is using it. It's become a very popular material out there, and more engines are coming out with it all the time. When you get it apart, the cylinder is going to have a very dark charcoal look, very black look. These are really neat coatings because, like molybdenum, it's very oleophilic. It holds oil like a sponge. The problem with moly on a ring, and especially in today's engines, Molybdenum doesn't really stick well to the ring. It likes to come off, and that's why moly is not used a lot in real thin ring stuff, or engines that have real high cylinder pressure. Detonation can be an issue. Things like that will knock the mollies out of the ring, and that's why the hard coatings, the PVDs, have become more common. They have better adhesion, they stick well, they follow the substrate surface of the ring better. They just kind of do a better job than moly. But moly does hold oil like a sponge. So that makes it, you can get away with kind of missing the cylinder finish a little bit with a moly filled ring. You don't have the RVK, the RK, you can kind of get away with a little bit. The moly holding an oil, cylinder's not perfect, but I've got this backup over here. It holds oil. We might be able to get away with it. With today's coating, the PVDs, and again, the importance of getting that cylinder finish right is they don't have the ability to hold oil very well. Most PVD coatings are only about 4% porosity. So we have to be sure that the cylinder wall does the oil retention. It has to do all the work. I can't count on the ring to do that. But we've come out with that same style of coating, but instead of it being on the ring, it's now on the bore. It's the plasma sprayed bores. Many of them have a moly base to them. Some use titanium, some have tool steel in them. But the one thing they have in common is they're very oleophilic. They hold oil like a sponge. These are going to hone glass smooth, literally mirror finish, almost no visible crosshatch whatsoever. This takes very, very special tools, typically 1,000 grit, 1,200 grit diamonds to try to achieve these types of cylinder finishes. So I'll say this about those types of coatings. If you're not equipped with that kind of equipment, or you're just not sure, you're better off to leave it alone. It's very easy to remove these coatings if you're not familiar with how to hone and how to process them. I was in Australia a couple years ago, had a gentleman holding a Mercedes blocks, and he comes to me. It was really, I didn't come there to talk about honing. It was about some other things, visiting their shop, talking about piston rings, of course. And gentleman came up from the back and said, "Hey, while you're here, take a look at this. Got all this black stuff coming up out of the cylinder." So we go in the back. He's got a 280 grit stone in a Mercedes block, 6.3 liter V8, and he's literally honing the plasma coating right out of the bore. He had no idea that he was doing that. And about a $10,000 block later, problem was fixed. So be aware of that coating. It's become fairly common today, a lot of it out there. And generally speaking, if you're not familiar with honing it, leave it alone. It's one of those coatings that doesn't really need a lot of help. Unfortunately, I had these slides out of order and just realized it. That's a surface finish of a freshly coated and honed Nikasil cylinder. As you can see down here, RPK is about a 6.9, RVK is 17, RK is 17. Now, we were looking at the numbers earlier for iron cylinders. Well, again, we're back to Nikasil being very oleophilic. It holds oil like a sponge. We can get away with an extremely smooth bore finish on Nikasil's Sumi bore, which is the picture you just saw before. That's the Sumi bore coating. Also done under the Flame Spray Technologies brand. There's quite a few different brand names, but all similar styles of coating. But Nikasil, we're looking down here at an RA of about a 6. Nikasil cylinders, you typically want to see them somewhere in an RA number, using that number, between a 4 and 8. Very, very smooth, not quite mirror smooth. Glass is usually around a 2, which is, again, we'll pop back about where you want to see these types of coatings. Mirror smooth, no crosshatch. To where Nikasil about a 4 and 8. These are becoming much, much more common coatings today than they were 10, 15, 20 years ago, though they've been around for quite some time. And this is Alucil. This is a hypereutectic aluminum. It's a silicon impregnated aluminum. It's been around for a long time. People remember it. The old Chevrolet Vegas were Alucil. This is not a coating. It's not a liner. It's what the cylinder is actually made out of. It's a silicon impregnated aluminum. There's a very specific process for Alucil. You can bore it, you can hone it, but you're going to, again, hone it glass smooth, mirror finish, no crosshatch whatsoever. There's a rouging process for Alucil. Sonnen offers it, Rottler offers it, quite a few different people offer it, but you're actually going to polish it to where it's glass smooth, no crosshatch whatsoever. Alusil is very common again today. BMW's using it, Porsche's using it, Audi's using it, Mercedes using it. It's coming back into favor because no liner required. It keeps the block very light. Weight's a big issue with the OEs today. This is not real common to see in race application stuff, but it has become more common and it is coming back. So, you know, the day of the iron cylinder is always there, but keep an eye out for some of these exotics because they are completely different beasts and you want to be careful when you're using them. Again, call us, ask us. Glad to answer any questions we can for you. Last couple things I'll touch on, and I'll let you guys get going. I know we're going way over here. Crosshatch angles. You hear the word 45-degree crosshatch angle, and that's what's referred to as the included angle. Again, I'm pointing at the screen. I should be using my pointer here. When you hear 45-degree, that's the included angle, the measurement between the up and the down. A 45-degree crosshatch angle measured off the deck is about 22.5 degrees off the deck. Let's see if I can, you can easily measure this. Let me see if I can find one of these here with a plastic protractor. I actually sell, or I should say sell, I give away, it's not for sale, I'll gladly give them to you, this little angle checker. It's got a clear backing. Get this out of here. I don't know if you can see that or not. 0 lines the deck. That's the crosshatch angle. So if we're looking at this line right here and that, you know, you put that on there and that lines up, matches, that's 20 degree. Well, that's a 40-degree crosshatch angle. And glad to supply this to any of you out there. Just a matter, either call us, drop us an email, gladly send you a crosshatch angle checker. You can pick up a similar thing at Hobby Lobby for about $1.86, but just a nice little plastic protractor that you can double check your crosshatch angles. And the reason we do this is because crosshatch angle helps to determine ring rotation speeds. If we get a real vertical angle, a real steep angle, it's going to try to make the ring rotate fast. And this can cause a ring to line up. Very quickly rotating ring can cause the end gaps to line up. Fairly common issue if you've got an engine that's always trying to line the end gaps up. More than likely, it's a crosshatch angle problem. Too up and down, too vertical. Flatter the crosshatch angle, the slower the ring rotation speeds. And this illustrates that. You can do a real flat crosshatch angle, and this one's not that flat. This is 28 degrees included or 14 off the deck. As we flatten the crosshatch angle out, you start to slow ring rotation speeds. But it also acts kind of like a dam. Flatter the crosshatch angle, typically the lower the blow-by numbers. More vertical the crosshatch angle, typically the higher the blow-by numbers. An easier pathway, an easier travel path up and down the bore. But the same can be said for oil. There's engines out there that have very long cylinders, very tall compared to the stroke. A more vertical crosshatch angle helps to get oil propagation up to the top of the cylinder. Perfect example is a Harley Davidson. A lot of Harleys from the factory run a 60-degree crosshatch angle. More vertical angle helps promote oil migration up to the top where they're not getting enough oil simply because of the length of the cylinder. Some of your flat engines, Subarus, Porsches, some of those will run a more vertical crosshatch angle, but not because they're trying to get the oil up to the top of the cylinder. They're trying to get the oil back into the sump, making it an easier pathway for the oil to move. As we flatten the crosshatch angle out, the oil wants to move side to side, not up and down. So as we flatten that angle, we can get, if we get too flat, into oil migration, and we can get a chattering or stuttering effect as the ring is going over that. It starts to kind of lump up like driving over a railroad track. So too flat of a crosshatch angle can create a problem. Too vertical can create a problem. Typically, most crosshatch angles in a high RPM, short stroke engine, you're going to see them somewhere between 30 and 36 degree included. Most of your general applications, you're going to be probably in the 40 to 45 degree included. And there are some applications out there that are going to be in the 60 degree range. Some of your Harleys are like that. Subarus, a lot of your Subarus, just about every factory Subaru cylinder I've ever measured is sitting at about a 60 degree crosshatch angle. That's not to say that they can't use something flatter, but based off what they're doing, they're about 60 degrees right out of the box. So again, handy little tool to double check your crosshatch angles. Again, there's the illustration of a 60, 30 degrees off the deck, 60 degree included angle. And with that, I want to say thank you for attending. Again, guys, I really appreciate this. I know we covered a lot of stuff very quickly. Hard to go into depth on every subject here. So please feel free to reach out to myself, Lake, any of the guys here at Total Seal. Glad to answer any questions you have. Send you a crosshatch angle checkers. We're here for you. We love the calls. We love talking to you guys. We love discussing gals. I don't mean to just say guys. We love talking to you because we want to help you. We want to know about your application. We want to know what it is you're doing and help guide you down the path to what is the right ring, what's the right cylinder finish, and how do we get it using your equipment? What do you have? You got a Rottler, you got a hand hone, you got a Sonnen. We can help guide you down that path. And again, thank you so much, everybody. I really appreciate you guys taking the time to watch this and attend today.
Super, thanks, Keith. I mean, excellent presentation. You're covering stuff that all the shops, I mean, we address this stuff on the tech line at AERA as well. And yeah, no problem going over. This is excellent information, very informative. And I do have some questions for you if you want.
Please, I look forward to it. Like Billy said, my favorite part.
Okay. So here's the first question for you. Are there any significant differences between an iron block cylinder and an iron liner in an aluminum block?
Well, if it's like for like material, if we're dealing with the same liner material as we are the block, no, they're gonna basically hone the same. The amount of oil retention of the material itself is going to be the same, but the aluminum, that's the next thing. How we're moving heat out of it. Iron block, iron sleeve into an aluminum block. The whole point is to get the heat, through the piston into the ring to the wall to the water to the radiator, and get the heat out. So there can be some difference in thermal transfer. Thermal conductance can be different depending on wall thickness. You are creating multiple layers of material that do move the heat differently. But as far as the actual surface of the material, as long, a 220 Bernal cylinder made out of the same material, whether it be the block or the liner, it's basically going to hone the same and produce the same type of surface. It's more about, again, how it's going to move, how it's going to distort because it's in an aluminum block, and thermal transfer. Those are going to be the differences.
All right, sounds good. Now here's an excellent question. So when using a profilometer, do you have to clean the cylinders from honing oil first when using the profilometer?
Yes, you do. And great questions, all of them, by the way. The stylus portion, and hang on just one second, because I just happen to have one sitting here. I have one sitting on the floor here. A gentleman bought used and wanted to get it set up and calibrated and working. This is the we'll say the work end of the profilometer. That little stylus, that little needle right there. And Billy again had earlier talked about skidding style and non-skidding style profilometers. This is a skidding. This little part of the housing right here is actually going to drag on the bore, and the little needle, the little stylus, is actually what's going to go down into the surface and give us that reading. These are, keeping in mind, relatively inexpensive in today's world. A Mitutoyo SJ210 is about $2,000. Again, there are profilometers out there that run in the hundreds of thousands of dollars. We have two of them here. Taylor Hobson, they're non-skidding style profilometers. We measure the face surfaces and the face trace profiles of all the real high-end rings, and used during production, and prototyping. They're non-skidding style, where this never touches the bore. The only thing that touches the tip. But to answer the question is, yes, it needs to be clean. We don't want any oils. We don't want any material in there, any debris. The debris or the dirt, the junk down in the crosshatch will give us a false reading. So you want it as clean as you can get it. But the other part is, these are a little potentiometer. And if we get fluid, we get oil, we get some of the nasty stuff inside there, this will stop functioning. And to replace one of these is about $400. Actually, a real good customer, good friend of mine, his name's Don. Don slipped while he was in the hone and dropped this whole thing in the tank. And we'll just say it don't work so good no more. So he had to buy a new stylus for it, which was I think $386 if I remember correctly, plus shipping. So bottom line, yeah, you want that to be nice and clean to get an accurate reading and to not create any damage inside here. Hopefully that answered your question.
Super. We had this question come in yesterday, and so this gentleman would like to know more information on gapless rings versus premium steel, At what point do you recommend customers switch over? Is it things like temperature ratings, durability on both, or how do you classify that?
Okay, no, excellent question. Well, and kind of two different questions, and so we'll answer both. The materials, like we talked about earlier in the program, are about temperature. A typical cast iron ring, and you could, if you had a heat treat oven, which we've got 3 of here, you can kind of play with this stuff, and it's kind of fun. You've got to look at how high the temperature is and how long you're going to sit at that temperature. But depending on the material, at some point in time, you're going to start to creep the metal. It's going to start to lose its tension. And again, for a ring guy, you think I'd have a million rings laying on my desk, but I'll use this one. When you look at a ring, you're going to have a free gap, this open gap. And sorry, this one's kind of not a great example, but you're going to have that free gap. And a great way to tell in an engine how the ring's performing is to look at the ring before you install it. File fit it, look at the gap, measure the gap, and write it down. So if you've got an application that's overheating the ring and it's simply getting too hot, you're going to start to see the gap close up. Let's say, for instance, that was 500 thousandths when it was new. You pull the engine down, it's not unusual to see the ring close up 100 thousandths or 80 thousandths. That's pretty typical. That's about a normal amount of creep in the metal. But if we start to see it doing one of these things, we're down 100 thousandths, 200 thousandths, or the tips don't line up. We've overheated the material. So depending on your application, we now have to look at what the ring was that we're using. Typical cast irons at about 1100, 1200 degrees for about an hour, you're going to start to do this to the metal. But if I take that same cast iron, and even though it's only been exposed to the temperature for a shorter period and take it to 2000 degrees, it's going to do this fairly quickly. So a great way to tell as far as what material you need for the engine is to let the engine talk to you, kind of be the, the ring or engine whisperer. Listen to what it's saying. Look at the parts coming out. Look at that free gap on the ring. And that's going to tell you a lot about the condition. If you've been using a ductile iron ring and they come out, the end gaps are great, free gaps are solid, it's not losing its tension, it's holding up well. Well, that one tells you that material's ability to handle heat is working for you. That's right for your application. Excuse me. And it also tells us you've got a good tune-up. If you've got, let's say, the best material in the world, the toughest thing known to man on the, this day and age on the third planet from the sun, and yet it's still coming out like this, that tells me you've got a tune-up issue. If you know you've got a good tune-up, plugs look great, it's not knocking the head gaskets out of it, everything looks great, but yet you're still creeping the metal, you're annealing it, you're taking the tension out of it, you need to upgrade. And that may be the pathway into steel. You may have so much cylinder temperature and are dealing with such a high heat environment, nitrous, turbocharged blower applications, you're simply generating so much heat, you're going to take the tension out of the ring. You have to move up into steels. And then we move into stainless steels, different carbon steels, tool steels, all depending on how much temperature. So looking at the ring coming out kind of gauges what material you need as far as from a temperature point of view. And again, you can also call us and talk to us, tell us about what it is you're doing, and we can make some suggestions. Now, as far as the gapless portion of it, the gapless, that's about eliminating that end gap. That's about eliminating that blow-by. That's about, in a normally aspirated engine, increasing the draw on the intake stroke. This is where the gapless really, really shines. By eliminating that gap, and keep in mind, everything we're doing here is trying to improve that ring seal. Right cylinder finish, getting the oil retention we need to keep the ring sealed, keep the scuffing off the skirt, keep this part lubricated, is all about improving that ring seal. And in a normally aspirated piece, it's about drawing air into the cylinder wall. Again, best camshafts, best fuel injection, best oil, all these things, best. If the ring's not doing its job on the intake stroke in a normally aspirated engine, we're going to lose some of that efficiency. So that's where the gapless really comes into play, is how much better it draws on the intake stroke, fills the cylinder better, gives you, as the tuner, the ability to do more, to do a better job, more air, more fuel, more power potential. Now, on the other side of it, into the blower, the turbo type applications, forced induction, the elimination of blow-by, keeping the junk out of the pan. And this does play as well in normally aspirated, especially in big fuel engines, mechanically injected alcohol, diesels, things where we're putting a lot of fuel through the engine. The gapless is really keen in keeping that fuel out. We're stopping it from getting down past the rings, down into the pan, killing the oil. The high performance diesel truck market today is on fire. We all know that. one of the biggest benefits I can do to that diesel is our gapless second ring. Not only does it have less blow by in the engine, but the big one is now it keeps the oil clean. You'll come back 5,000 miles later, go to change the oil. Guess what? Still looks like oil. Doesn't look like black coal because it kept all that fuel out of there. So kind of two different questions there. Hopefully that answered it for you.
Super. Thanks, Keith. So we got time. We'll ask one or two more questions, and then we're going to lead into presentation number 4. Just so everybody knows, we do have prizes to give away, and we will have time at the end on our final wrap up. So do hang on to make sure that you hear your name called for a prize. And so Keith, this one comes up all the time too. They've mentioned they've seen hot honing. They don't use it, but they're wondering how much of an influence that the temperature of the bore is measured and how much of an influence hot honing actually makes.
Well, that's an excellent question, and thank you. Hot honing is really neat, but it creates its own set of issues. I'm a big believer in anything that we can do to help replicate or duplicate that operating condition. You know, if that engine's running at 200-degree water temperature, I want to try to get the inside of that block up to 200 degrees. If it's got a bell housing bolted to it, why not have a bell housing bolted to the block? If it's got 2 cylinder heads, why not have the other head? I want to try to replicate everything I can because just tightening the fasteners up on it can move things around quite a bit. So yes, I'm a big believer in hot honing. I think it's a great thing to do. The problem with it is, one, you've got to have a hot honing system. And depending on how you're doing it, it can create some kind of honing issues. If you're using one of the CK engineering machines, which is a great system, it's heating the honing oil itself up. So you're not only circulating that hot fluid through the block, which helps to mimic that cylinder distortion, you're also running 200-degree hot honing oil on you as the operator. So there's some things that kind of come in with hot honing. You are and run the potential of having 210-degree liquids thrown at you and splashed on you while you're honing. So that's kind of the downside is dealing with that hot environment. But the upside is it does help to move the cylinder and replicate it as much as possible into the operating world. So like I said, I like it. I think it's a great idea. But from an operator point of view, it does have some drawbacks. So that one kind of comes to you of what you like to do as far as the additional equipment that's required to do it. And do you mind 200-degree hot stuff getting thrown on you?
Yeah, no kidding. All right, I'm going to ask one more question, just because this particular question pertains to, I think, just about every shop, and it's always a question that comes up as well. So, Keith, what are your tips for getting all the honing grit out of the cylinders after honing?
Wow, that's we'll say clean. The process that I use myself, and it works pretty darn well, but it's a lot of steps and a lot of stages. Probably what a lot of people do is after the honing, after we're done, I'll come back in with a very high detergent oil. A lot of people like to use transmission fluid, but a very, very high detergent oil on a brush. The old cylinder, cleaning brushes. Myself personally, I've got the old Moroso cleaning brush kit, and I'll come in there with something, of that nature, very high detergent to get in for my initial clean, scrub it out as best I can, get that fluid in there, trying to float that honing junk up out of the crosshatch, get that oil in there, something again that's very detergent, wants to clean, lift that abrasive, lift that gunk, that junk back up out of the cylinder. I'll then wipe it back down, get it good and clean. I then come back in with a good hot soap and water. The screen just flipped and now I'm looking at me, so it kind of freaked me out. I'll come back in with a very high surfactant detergent, something that's a very, very foamy, bubbly. The bubbles that are created in a soap are the surfactant. And surfactant is what helps to lift the junk up out of the hone, out of the crosshatch. So a very foamy, bubbly, hot water solution. I'll come back in, scrub it out with that. Once I've done that, I wipe it back down. Then my third step is I'll come back in with a good lint-free towel. Personally, again, I use those blue Scott towel that you get on a roll. You can buy at Home Depot, any good hardware store. I'll come back in with a clean solvent, a clear solvent, like a lacquer thinner, brake cleaner, something that flashes off really clean, really quick. I'll wipe that back down, and I leave the towel, let it sit there, let the solvent flash off. Once it's flashed off, I look at it. If it's clean, there's nothing on the towel, I know my cylinder's clean and I'm ready to go to assembly. But if I've still got, and it'll kind of leave a brownish stain, if I've still got kind of that brownish stain on the towel. I'm not done. I come back in with my hot soap and water, scrub it out again, and we'll say wash, rinse, and repeat. But normally, I'll start off with an oil like a transmission fluid. Again, I'm old school. It's how I was taught, but it always seemed to work. And I come back with a very, very foamy, high surfactant, real bubbly Dawn dishwashing liquid. Always worked very, very well. Hot water, scrub it out, clear solvent, and that'll almost always get it for me.
All right, excellent, excellent, super, Keith. Thank you. Very good presentation. Everybody, we still lots of questions coming in, and what we're going to do is we're going to bring on Ben now, and but what we'll do is, like I say, we're going to do a final wrap up. We're going to have all four gentlemen. They're going to be on the end. We'll have about 45 minutes to kind of wrap things up at the end. So if there's any more questions you had, or if there's any more questions that we didn't get to, we'll definitely get to those at the end. So what I'll do now